In this video and in the next video, we're going to talk about adding vectors. And adding vectors can be accomplished by several different methods. The introductory methods that we're going to deal with, that most physics classes deal with, are going to be the graphical methods of adding vectors. And these do have some benefits, but they also have some drawbacks, and we'll discuss that at the end of this video. The first method that we will encounter is the parallelogram method, and then we will look at the tip-to-tail method. Both of these are the graphical methods for adding vectors. In a subsequent video, we will look at the component method, where we use our skills in resolving vectors into their corresponding unit components, and then we're able to add them mathematically or combine them mathematically, which has a lot of benefits to it. So to begin with, let's look at the parallelogram method. And as an example, let's take two vectors A and B. And these are force vectors. We'll just use that as a general example. So vector A is 20 newtons of force directed at 45 degrees on the unit circle. Vector B is 40 newtons of force directed at 135 degrees on the unit circle. And then we're going to introduce a concept known as the resultant vector, which is the vector that is derived from the addition of two vectors. And we're going to denote that as vector R, as you see here. So for the parallelogram method, the first thing we're going to do is we're going to take and we will graph our first vector, vector A, and this is it right here, with 20 newtons of force at 45 degrees. And so this is approximately 45 degrees here. I would normally use a protractor and a ruler to get as good of graphs as I could possibly obtain, but for the purposes here, this will suffice, and this will also help prove one of my points. In the parallelogram method, we actually join them tail to tail, and so we're going to put vector B in at 135 degrees, and it is 40 newtons. And so the magnitude, which corresponds to the length of the vector graphically, should be approximately twice, or should be exactly twice what the vector directed at 45 degrees is. And so we see here that we have approximately 135 degrees on the unit circle. And if you look at this, I've gone to as good of effort as possible to try to represent that this one is twice the magnitude of the other one. Now for the parallelogram method, what we do next is we construct a parallelogram. And we do so by completing the square here, just as we would if we were drawing a geometric shape. The resultant vector is found by essentially finding the diagonal of the parallelogram, as you see drawn in green here. And this is the approximate net position of the force. In other words, if we exerted two forces independently, one 20 newtons at 45 degrees and one 40 newtons at 135 degrees, it would have the exact same effect as exerting this force in green, whatever magnitude it happens to be, at that approximate direction. The problem here is that, as you can see, depending on the instrument that you're using, your accuracy is limited. But that is how we would do this as far as constructing a parallelogram and identifying the appropriate resultant. Now, the tip-to-tail method works a little bit differently, and it is one step shorter. However, it is prone to some of the same issues. Initially, we're going to look at our same set of vectors for comparison. So with the same vector A and vector B directed with the same magnitudes and in the same directions as our previous example, we will lay in our first one in the exact same way that we began our previous example. But at this point, what we're going to do is we're going to come to the head of this vector, and we're going to draw just a little marker set of coordinates. And we're going to use that now as our reference point to add our second vector in, and we'll add that vector 135 degrees on the unit circle from this point right here. And so as you can see, the tip of one vector is connecting to the tail of the next one, and when we put that vector in, this is what we get. Now our resultant vector R is drawn from the tail of the beginning vector to the tip of the final vector. This has some benefits over the parallelogram method in that I can do this for any number of vectors and then draw the final resultant in one graphical motion, as opposed to having to do multiple independent parallelograms with each subsequent resultant. So this one here does give us a graphical representation. It is approximately the same as the graphical representation that we obtained from the parallelogram method. So let's look at the benefits of each individual method. One, parallelogram method and the tip-to-tail method are both very quick, and in doing that they give us a visual reference of exactly what our vectors are doing. However, these are prone to error, specifically human error, in that the amount of care that you take in drawing this is going to determine how accurate your resulting vectors are. Let's go back and look at this, and I will emphasize a couple of points. Regardless of whether I use the parallelogram method or the tip-to-tail method, when I draw this out, at least in principle, the length of the physical drawing of the resultant vector should correspond to the proper length of the resultant vector. And so when I draw these in and then I measure the resultant vector, I should get as close as possible to the actual mathematical value of the resultant vector. And it should be at the approximate, as close as possible within the limitations of the instruments, to the true direction of that vector. But human error does play a big role in this, in how much care we take, and even physical limitations such as eyesight and dexterity of the fingers in drawing these things out. It does have limited utility in that it becomes impractical specifically after dealing with more than 2 vectors on the parallelogram method and probably about 4 vectors on the tip-to-tail method. The utility is just very, very, very limited. And then finally, our instrument accuracy is also a big issue when it comes to measurements on the ruler that we're using, even down to how sharp the pencil or pen tip is. All of these things factor in and can contribute either small or sometimes very large errors into this particular method. So we use these sometimes to get a good idea of where our resultant is going to be in order to check our mathematical calculations that we'll use when we add vectors via component form in the next video.